Hello everyone, this is Nitin Kumar Sharma from Kumar Engineering College, Ghaziabad. I am an assistant professor in Department of Applied Science and Humanities. Here we take mathematics, and today the topic of the lecture is vector differentiation, and this topic belongs to the module 5 of Engineering Mathematics first. Paper code is BAS103 for the AKTU. So the content of this video lectures are the gradient of scalar point function, divergence of vector point function, curl of vector point function, application of above topics, directional derivatives, question based on the above topics. Then the reference books are AKGEC, Advanced Engineering Mathematics, John Wiley and Sons, 2005 edition, Morris DeVere, and this is the book from the Pearson, and B.V. Ramana from TMH, B.S. Gewal from Khanna Publishing House, and here is the first definition of the topic. The point function. So what is a point function? Firstly, we should understand. The point function can be defined by a variable quantity whose value at any point in a region or space depends upon the position of the point is called a point function. So here we want to say that a point function is defined over a space, a region of the space, and it will give you some value on a particular point of the space. Then there are two types of point functions. The first is scalar point function, second is vector point function. So the very first discussion is over. The scalar point function. The scalar point function can be defined as if each point p, x, y, z of a region are in space, then there are corresponding a unique scalar function fp, then this fp is said to be scalar point function. Or we can summarize it like that, the function defined over a scalar field is known as the scalar point function, and this is depending on the points of the scalar field. The next is the examples for this function, so that the temperature distribution in a field or the space. So the temperature distribution in a heated body is an example of the scalar point function. Density of a body is another example of scalar point function. Potential due to gravity are the example of the scalar point function. See, if you want to determine the temperature at any point in the given space, or in a space in a room, at a point in a room, then this is a scalar point function, and the value of the temperature will be the value of the scalar point function. Now, the vector point function. If to each point p, x, y, z of a region R in space, there corresponds a unique vector fp, then f is called a vector point function. That means if a field is a vector field and the function defined over it is a vector point function, which gives you a vector value over any of the point of a vector field, vector space. The velocity. This is the example. The velocity of a moving fluid. The velocity is a vector function of a moving fluid, and the gravitational force are the examples of the vector point functions. Because when a fluid is moving in a channel, through a channel or a pipe, you can say, then the direction is also fixed with the magnitude of the velocity, which is speed of the fluid. So now the next is vector differential operator. This is an important operator which we will use to differentiate the vector quantities or the vector functions. The first is the vector differential operator. It is the definition of it. The vector differential operator del is denoted by the symbol this triangle. See, this is the symbol of the differential operator, vector differential operator del. Okay, differential operator del can be defined mathematically by this simple vector form. You can see this is the del operator, the symbol, and here are the unit vectors along the axis x for the axis y and z, I, j, k, and these are the differential operator corresponding to the component of a function in direction of x, y, and z. Alright, then next is the gradient of a scalar function. Before moving to this, let me discuss one thing also. This vector operator is also known as nabla, but it is not in the common practice. We can call it del. The gradient of a scalar function. The gradient of a scalar function. So if phi be a scalar function and it is defined over a scalar field, then its gradient is denoted by grad phi. See, this is the notation for the gradient of a scalar function. Okay, and it is defined mathematically by grad phi. Grad phi, and here you can see the grad phi is equal to the simple product of grad, that means del operator, and the given function phi, given scalar point function. It is also equivalent to the notation this. It is also equivalent to this. We can say this is the grad phi. See this. This is equivalent notation. Next, the example. The example for this theory are, first of all, for the gradient of the function. If phi is equal to 3x square y minus y cube z square is any given scalar point function, then we have to find the grad of phi. At any given point, the point is 1, minus 2 and 1. Then the solution is given by grad of the phi and is denoted by the del phi. Then the definition of the del phi, del was this operator and the definition of the function is 3x square y minus y cube z square. So now we have to operate it over the components, and then this part will be distributed over each of the term. Then you can see the phi is distributed over each of the term, like this. You can see here the phi is distributed over each of the term. Okay, then see, now after distributing the function over these terms, we get the differential, partial differential with respect to x. Firstly, you get 6xy. Then with respect to y, this is the expression, and with respect to z, this is the expression of the differentiation. Partially differentiated parts are these, and then components are solved. We got grad phi. Now this was the general gradient phi. That means it is a vector. Actually, it is a vector. Gradient phi is a vector. So now it is a general vector or the gradient of a given field defined by this function, and now at a particular point which was given to us, the particular point given to us was 1 minus 2, 1 minus 2 minus 1. So at this point the gradient is defined by substituting the values of x, y and z in the general function, general vector. So these are the values substituted in place of x, y, z, and we get the vector at the given point 1, minus 2 and minus 1. Okay. Then geometrical meaning of gradient. The geometrical meaning of gradient is the equation phi xyz equal to c represents a family of surfaces for different values of constant c. Then this notation grad phi, that is del phi, is a vector normal to the surface phi xyz equal to c. If we have the surface phi xyz equal to c, then its vector normal vector is given by del phi, that is gradient of this surface. Now another example before moving to this, if phi xyz is any surface, then defined by phi, then the normal vector is given by the gradient. So if we take the gradient of this phi, then the vector we got like this will be perpendicular to the surface phi. Okay. Then the example for this is find the unit normal vector, unit normal to the surface x y cube z square is equal to 4 at the given point minus 1, 2. Now first of all we are given with the surface. This is the surface and this is the point given to us, and we are to determine the unit normal vector. So in this sequence we have first to determine, if we want to solve it, we have first to determine the vector, the normal vector to the surface. So we will write the phi xyz is equal to xy cube z square is equal to 4, and then see, this is the discussion we have done earlier, that we know that del phi is the vector normal to the surface phi xyz is equal to c. Then the mathematical definition given by this normal vector is del phi, then the components with distributed phi, and then here we have distributed the vector, distributed the phi over the different component of the vectors, and then after differentiation we get this vector as normal vector. Sometimes we also denote it by n, vector n. Okay. So then the normal vector at the given point, because this was the vector at any point of the surface, and the normal vector to the surface at any given point minus 1, 2 is by substituting these values of, this is a value of x, y and z. While we substitute these values in the general vector, then we will get this vector, and this is the particular vector at the given point. Now the question was to determine the unit normal vector at the given point. So earlier we have determined the normal vector only. So while we substitute the values, we got the particular vector at the given point, and then to convert it into unit vector, we are dividing the vector by its magnitude. So this is the vector, and we can say that this was vector n. So we have to divide it by magnitude of it. Okay. Then we got this kind of mathematical calculation, and this is the magnitude. This is the magnitude of the vector, and after division you get the expression like this, which is the unit normal to the surface at the given point -1, -1, 2. So this was the example for the unit normal. Another example, another application of the gradient is to determine the angle between two surfaces. So if we have two surfaces, like suppose this is a surface and this is another surface. So if you want to determine the angle between these two surfaces, then the theory is to determine the normal vector to both of these surfaces. So first of all, we will find, suppose this is a surface and this is another surface. We want to determine the angle between these two surfaces, so we have to determine the normal vectors to these surface. This is n1, this is n2. Okay, and if you want to determine this angle theta, then the same angle will be here. The same angle will be here at this point theta. Okay, so this n1 and n2 can be determined by the gradient of these surfaces, and is given by the divergence of these functions, these expressions. So now let us start the solution. Here we have the first surface. We have first surface with the equation 1 and the second surface with the equation 2. Okay, then the normal to the first surface. Here we have used the notation in place of n1, this. So you can say either small n1 or the theta you can use. Okay, so theta, whatever you want to note, but usually we take for the normal n. Okay, this is n1 and is given by the gradient of the given surface first, and the first surface was x square plus y square plus z square minus 9, and the del of it is given by this expression. And you can see after differentiating of the components with respect to x, y and z, we get, firstly, when you differentiate it with respect to x, you will get 2x. When you differentiate it with respect to y, you get 2y, and z with respect to z, then you will get 2z, because all other parts in case of the partial differentiation will be 0. Okay, so you will get this kind of normal vector, which is denoted here by n1. Okay, small n1. So now at the particular point 2, -1 and 2, the vector is 4i minus 2j plus 4k. These are the notations for the normal vector for the first surface. Then the normal to the next surface, normal vector to the next surface is n2. N2 is given by the del of the second surface. Second surface is z minus x square minus y square plus 3. Then operate the definition of del, that is the vector differentiation, scalar differentiation for this, and then you will get the result like this. Corresponding elements will be differentiated partially with respect to x, y and z. Then see, this is the result after differentiation, but when we substitute the values of the given point of x, y, z, then we will get minus 4i plus 2j plus k cap. Alright, this will be the equation number 4. Now the aim was to determine the angle between these two surfaces, and the angle was theta. So this was our strategy to determine it. Now we have determined these two n1 and n2 normal vectors, and then we are going to apply the formula for the angle between two vectors given by n1 into n2 is equal to magnitude of n1 and n2 and cos theta. So while we are working for the angle, so we are taking cos theta is equal to n1 dot n2 divided by the magnitude, product of the magnitude of n1 and n2. Alright, so here we have the dot product of the vectors and then the product of their magnitude in the denominator, and after solving the dot you will get minus 16, and after multiplying the magnitudes then you will get 6 root 21. After solving this you will get the result, the angle theta is equal to cos inverse minus 8 upon 3 root 21. So finally you got the angle between two surfaces, cos inverse minus 8 upon 3 root 21. Alright, so this was the angle between two surfaces. Now next application of the vector differentiation is directional derivative. So what is the directional derivative? Directional derivative is the component of del phi in the direction of a vector is called the directional derivative of a vector of a function phi, that is scalar function phi, in direction of the given vector. Okay, so mathematically the directional derivative is given by phi del of phi, that is gradient of phi, and dot product with the unit vector of given vector A. So in the case of determination of the directional derivative, we have to take dot product of the gradient of the given surface and the unit vector given by a vector A. This vector will be given to us to determine the directional derivative. Now, use of the directional derivative. The directional derivative is the rate at which the function changes at a point in the direction of a given vector. If we are to find the rate of change of the given function in a specified direction, we shall calculate the directional derivative. Then, this is the example to understand that how we can calculate the directional derivative. So, we are given with a function phi xyz, which is an equation of a surface, you can say, at a point 1, minus 2, 1 in the direction of the given vector 2 I cap minus j cap minus 2 k cap. This is the vector, and this is taken to be vector A. Alright, so let us start the solution. So first of all, we will write the given function as phi, given surface as phi, and then firstly we find the normal vector to the surface, that is gradient of the surface, and is operated by the del of the given surface. Then after solving the partial differential of this phi by distributing this phi over each of the component, then we will get the result like this. These are the derivatives in the direction of the coordinate axis, and then we will find the gradient of the phi at a particular point, that is the normal vector at a particular point, after substituting the value of x, y, z, and then after finally solving, we get this as the normal vector to the surface, that is the gradient of the given surface, which is j cap plus 6 k cap. Then, before moving to this slide, let us see. This is the vector n and is normal to the given surface phi. It is normal to this surface. If phi is the surface, then the n will be normal to this. Okay. So then, if you want to determine the directional derivative, then we have to determine the unit vector of A. So A was given to us, vector A was given to us. So we have to determine its unit vector, and then unit vector is given by the division of the magnitude to the given vector. So we get the result like this, and then so the required directional derivative at the given point 1 minus 2, 1 is the product of the gradient, that is, which was n at the given point, and the unit vector which we have solved here, and now taking the dot product of these two, and after taking the dot product of these two, you will get the result like this, and finally solving, we will get minus 13 upon 3. Minus 13 upon 3 is the directional derivative at the given point for the given function, a given surface phi. So now, next application is to determine the maximum value of directional derivative. That is the mathematically directional derivatives is given by this definition we have discussed earlier, where A is the given vector and then its unit vector is A cap. Then we know that it is the dot product of two vectors. So therefore, it is maximum when the both vectors are parallel to each other. Therefore, we take the directional derivative in the direction of vector, unit vector A for the given vector A. Okay. So these two vectors should be in the same direction, and in this case, this will give you the maximum magnitude. Okay. Therefore, the maximum value of the directional derivative occurs when the direction of the both vectors are same, and the direction should be in this direction. So the maximum magnitude of the directional derivative of phi is the greatest rate of increase of phi and is given by the magnitude of del phi. Okay. Now the example for the greatest rate of increase is given by, so we have to find the greatest rate of the increase for the given function phi. This is the function x square yz plus 4xz square at the given point 1 minus 2 and 1. Now, first of all, we will define the function as phi xyz, which is x square yz plus 4xz square. Then firstly we will find the gradient of this function, and after finding the gradient of this function, as we have said earlier, discussed earlier, we will get this kind of structure, mathematical structure, and then because this was the general vector. Now we have to determine the particular vector at any particular point of the surface phi, and that particular point is given to us as 1, minus 2, 1. After substituting these values in the general vector, we get this calculation, and after solving it, we get 1 j cap plus 6 k cap, where x component is missing. I mean to say it is 0. So either we can write it like this or we can omit it. So then, to determine the greatest rate of increase, we have the formula. To determine the modulus of the del phi, and we get this kind of structure, and after solving we get root 37. It is the greatest rate of increase. Now the next is divergence of a vector. So it is another application of the vector differentiation, and now we are moving toward the vector functions. So the divergence of a vector point function. Divergence of a vector point function is defined by divergence of f, and is also denoted by del dot f, and this is the definition of del. This is the definition of given vector. Now we are taking dot product. We are taking dot product of these two vectors. After taking the dot product, we get this kind of structure, and this is what we call the divergence of f. And then you can see it is scalar point function now, because the divergence of a vector function is a scalar function. This shows that the operator del converts a vector function, if we take dot between these two, into a scalar function. So this is the application of, this is another application of del, operator del over the vectors. And then physical meaning of divergence. So physically, the divergence of a vector quantity represents the rate of change of the field strength in the direction of a field. If the divergence of a vector field is positive at a point, then something is diverging from a small volume surrounding the point. And if it is negative, then something is converging into the small volume surrounding that point. If the divergence at a point is 0, then the rate at which something is entering a small volume surrounding that point is equal to the rate at which it is leaving that volume. These pictures are clarifying it, that if the divergence is positive, then something is moving outward from the small volume, and if something is converging at a point, then it is negative divergence, and here the rate of inlet is equal to the outlet, then it is zero divergence. This picture is showing what we have stated earlier, that something is moving this channel is at this point it is zero divergence. Okay, so now find the divergence of vector. So coming to the mathematical application, this is the vector we are given with, and we have to determine the divergence of this vector function, and the vector function is defined by vector f is equal to x z cube I cap minus 2 x square y z j cap plus 2 y z raised to power 4 k cap. So if you want to determine the divergence of this function, then we will use the formula del dot F. The notation is also defined by the div of F. Okay. So when we operate the del operator, okay, when we operate the operator del F, when we operate the operator del over the F, then we get the structure del F1 over X, del F2 over Y, del F3 over Z. That means in the case of the divergence, we have to distribute the given function over the del operator, and simply we have to differentiate the given function with respect to X, then plus, then with respect to Y, then plus with respect to Z, and sum these components. And after summing these components, we get the result, which is the divergence of the vector F. Okay. Now, the solenoidal vector. This is another application. Solenoidal vector. The vector field whose divergence is 0 is called solenoidal, which we have discussed earlier in the last slide. Like this. At this point, the vector is solenoidal. At this point. Now, how we can show the vector is solenoidal? If we have the vector V and we have to show it the solenoidal, then we have to take its divergence, and if we take the divergence of it, then we have to solve it like we have solved the vector F, and then differentiate with respect to X, then Y, then Z, and sum all these. Okay, and after summing you will get 0. You can see if we differentiate with respect to X, there is no X, so this is the 0 component. With respect to Y, there is no component, and if you differentiate with respect to Z, there is no component for no value for Z, so the result is 0. Then finally we got 0, and this is a null vector. This is a null vector. Hence, sorry, this is not null vector actually. This is a scalar value, and we will get the vector is solenoidal vector. Okay, so the final application of the del is the curl. The curl of a vector point function is defined by the cross product with the operator del, and is solved by the distributing this over this operator with the help of the determinants, as we usually solve the cross product of the two vectors, and we get this kind of structure, which is also a vector. So curl of a vector also give you vector, two vector. That is, sorry, the statement is corrected here, that if you want to take the curl with the del, so del return you vector of a vector. Okay, so the next is curl F is the vector quantity, and the example of it is we are given with a function, vector point function at a point -2, 4, 1, and then the solution of it is given by, this is the vector point function, taking the curl using the formula of and solving with the determinant. See, these are the components of the given vector, and when we solve it using the process of the determinant, and then you will get this kind of value, and we got this vector, and which is the curl of the given vector F. Okay, so this was the general vector. Therefore, now to convert it at a particular vector at a given point -2, 4, 1, we will put the values of x, y, z into the curl of F. Then we will get the -j plus 2k cap. Okay, so this was the curl of a given vector. So if these are the physical meanings of curl. The curl measures the extent of the rotation of the field about a point. Okay, so visually you can see these are the pedals in a fluid, and the rotating vector is the normal vector. So this shows the curls of this vector, which are normal to the this vector field, okay. Then if the curl f is equal to 0, then the vector is irrotational. The rotations are 0 because meaning of the curl is rotations. Rotations means curl. So if the curl are 0, then the vector f is irrotational. Okay. So this is the vector and application of this theory, and is if you find the curl of this f, you will get this kind of structure. And here he is saying that you want to determine ABC. So because this vector is irrotational, so determine the curl of it, and then putting this curl is equal to 0 because the vector was irrotational. So if we got this equal to null vector, and then by comparing the components we get the value of ABC. Okay, thank you very much.